This is the third video in the Chemistry Key Skills series for the new GCSE 9:1 Science specifications. In this video, we will be looking at bonding. This will include ionic, covalent, and metallic bonding. In this video, we will look at what an ion is and how it is formed. We will draw dot and cross diagrams to show the formation of ionic and covalent bonds, and we will look at the structure and properties of simple ionic, simple covalent, giant ionic, giant covalent, and metallic bonding. For the big question today, we need to be able to compare the properties of ionic, covalent, and metallic bonding. So far in this series of videos, we have only looked at atoms. However, atoms can lose or gain some electrons in order to become ions. All atoms want to get a full outer shell, as this will make them stable. In order to do this, they need to change the number of electrons that they have. The metals and hydrogen need to lose electrons to get a full outer shell. This is because they have 1, 2, or 3 electrons in their outer shell. When they lose these, they gain a charge of +1, +2, or +3, dependent on the number of electrons that they have lost. This is also equal to their group number. So group 1 elements form 1+ ions as they lose 1 electron. Group 2 elements lose 2 electrons and so become +2 ions. As these are positive ions, these are known as cations. Nonmetals, however, gain electrons to get a full outer shell. This time, their charge is dependent on how many electrons they need to gain in order to get a full outer shell. Group 5 elements will gain 3 electrons and become negatively 3 charged. Group 6 will gain 2 and become -2 charged, and Group 7 will gain just the 1 electron to become negatively charged. For example, fluorine would become F-. Negative ions are known as anions. Ionic bonding is the first type of bonding that we will look at. This happens between a metal and a non-metal, and happens when they transfer electrons from one to the other. This makes both of the atoms into ions. The oppositely charged ions are then strongly attracted to each other by electrostatic forces, because one is positive, the other is negative. This attraction is called an ionic bond. Because the charges cancel each other out, this means that the ionic compound is neutrally charged. Because of this, we can work out the overall formula using the charges. For example, the formula of sodium chloride would be NaCl. Sodium loses 1 electron to become Na+. This electron is transferred to chlorine, making chlorine Cl-. We have 1 positive charge and 1 negative charge, meaning overall we have a neutral charge. For magnesium chloride, magnesium is in group 2, so it would form a +2 ion. We would then require 2 chlorines in order to neutralize this, giving us the ionic formula MgCl2. An easy way to show this transfer of electrons is using dot and cross diagrams. This is something you can be asked to do in your exams. If we take our previous example of sodium chloride. So sodium is in group 1, so we know it has 1 electron in its outer shell. From the previous tutorial video, we also looked at its electron configuration. So sodium is 2, 8, 1. It has 2 electrons in its inner shell, 8 in its middle shell, and 1 in its outer shell. Chlorine, on the other hand, is in group 7, so we know it has 7 electrons in its outer shell. Again, looking at the periodic table to work out its electron configuration, this gives us a configuration of 2, 8, 7. So 2 in the inner shell, 8 in the middle shell, and 7 on its outer shell. As chlorine only needs 1 electron to complete its outer shell, and sodium needs to lose 1 electron to complete its outer shell, its electron is going to be transferred. As sodium now has 1 less electron than it does protons, it will become positively charged. To show this, we draw square brackets around it and put a positive sign. Likewise for chlorine, we will draw in our square brackets and put a negative sign. We have now completed our dot and cross diagram for sodium chloride. The new electron configurations would be 2, 8 for sodium. I now want you to practice drawing lithium chloride, magnesium oxide, and magnesium chloride. Ionic compounds always have a giant ionic lattice as their structure. In this, the ions form a closely packed regular lattice. There are the very strong electrostatic forces between the oppositely charged ions. These go out in all directions. You can see one here, both in the 3D model as well as in the ball and stick model. Ionic compounds all have very similar properties. They are all solids at room temperature. This is because of the very strong forces of attraction between each of the ions. It takes a lot of energy to break this force of attraction. Solid ionic compounds don't conduct electricity because they don't have any free movement of the ions. However, in the molten state, so when they've been melted or when they've been dissolved in water, they can conduct electricity as these ions can move. They will also dissolve very easily into water. For example, sodium chloride, common table salt, easily dissolves into warm water. Before we move on to covalent compounds, it's important to note that these visual representations of molecules aren't fully accurate. We're not showing the shape of the atoms, we're not showing the exact bond directions. As such, these give us a very basic visual representation of what the bonding looks like, in particular how the electrons have been moved. Our second type of bonding is covalent bonding. This type of bonding only happens between 2 non-metals. As both non-metals need to gain electrons in order to get a full outer shell, the electrons cannot be transferred. Instead, to form a covalent bond, a pair of electrons is shared between 2 molecules. This shared pair of electrons is a very strong bond. However, the forces of attraction between each covalently bonded molecule is very weak. Due to these weak intermolecular forces, the melting and boiling points are very low. As such, most simple covalent molecules tend to be liquids or gases at room temperature. They do not conduct electricity because they don't contain any free electrons or ions, so simply can't pass on that electrical charge. As with ionic bonding, we can draw dot and cross diagrams. However, this time the electrons are going to be shared rather than transferred. If we take the simplest covalent compound, which is hydrogen gas H2, this is made up of 2 atoms of hydrogen. As we know, hydrogen has 1 electron in its outer shell. This means it needs to gain 1 electron in order to become stable. As both hydrogen atoms need to gain an electron in order to become stable, they do this by sharing 1 electron each. This sharing of 1 pair of electrons is known as a single covalent bond. You can get more than 1 covalent bond. For example, for O2 oxygen, both oxygen atoms need to gain 2 electrons. As such, they share 2 pairs, forming a double covalent bond. Nitrogen requires 3, therefore it forms a triple covalent bond. We can also do this to draw molecules, for example, carbon dioxide, CO2, or methane, CH4, or water, H2O. I want you to practice drawing these by drawing O2, N2, H2O, CH4, and CO2, drawing only the outermost shell. Here we have the 5 completed covalent diagrams. We have O2, which we can also write as O with a double line, so an equal sign O, to show that we have a double bond. For hydrogen on the previous slide, we could write this as H-H. Nitrogen, which we have N with 3 lines M. We have CO2, which has 2 double bonds. We have water with 2 single bonds, and methane with its 4 single covalent bonds. Simple covalent molecules can be joined together to make polymers. For example, polythene. These are hydrocarbon chains made up of repeated monomers of each carbon bonded to hydrogens. By repeating these monomers, we can make much larger molecules in order to carry out a wide range of functions. Some covalent structures are much larger. These are known as giant structures. They have all of the atoms bonded to each other by very strong covalent bonds. They have high melting points as there's lots of energy required to break all of those bonds. One of the ones that you need to know about is able to conduct electricity, which obviously covalent compounds usually don't. They do not dissolve into water, and you need to know the following 3. All of them are made up of carbon. The first is diamond, the second is graphite, and the final one is graphene. Despite being made exclusively of carbon, these 3 giant covalent structures have very different properties. In diamond, each carbon atom is covalently bonded to 4 others. This means that there are no free electrons. It is very strong and it has a very high melting point. Because of this very strong structure, it is able to be used for cutting tools and for drilling, and it doesn't conduct electricity. Graphite, on the other hand, is again only made up of carbon. However, this time each carbon atom is bonded to 3 others. This leaves 1 free electron. It has a high melting point, however, is quite brittle. This is because it is formed in layers which can slide over each other. These layers enable it to be used for pencils or as a lubrication. Because it has free electrons, it is also able to conduct electricity, meaning we can use it in processes such as electrolysis. Finally, we have graphene. Graphene is like a single layer of graphite. It is a sheet of carbon atoms that have been joined together and can be used for fullerenes and nanotubes, which we will look at in more detail on the next slide. Diamond, graphite and graphene are examples of carbon allotropes. You also need to be able to talk about fullerenes. These are molecules of carbon that are shaped like tubes or balls that we can use within medicine. They're mainly made up of the graphene that we looked at on the previous slide. In particular, looking at carbons that are arranged as hexagons, pentagons, or heptagons. This effectively acts as a cage for other molecules, so we can put other molecules inside of the fullerene in order to deliver it to a certain cell. For example, in medicine, we could put a drug inside there. They have very large surface areas, and so they can be used as catalysts in order to speed up other reactions. 2 examples are Buckminster fullerene, or the buckyball, which has the molecular formula C60. It's made up of 60 carbons. It's a hollow sphere, and as such we could put something inside of it. The other option is to use it as a nanotube. So again, these are tiny cylinders of graphene, so they don't conduct electricity, but they're very high tensile strength. We can use these to make things like tennis rackets and Formula One cars. Another good example of a giant covalent molecule is silicon dioxide. This is also known as silica. It has a giant covalent structure made up of silicon and oxygen. As we can see, each silicon atom is covalently bonded to 4 oxygen atoms, with each oxygen atom covalently bonded to 2 silicons. This gives it the formula of SiO2. It's very hard, has a high melting point due to these strong covalent bonds. It does not conduct electricity as it has no free electrons. The final type of bonding you need to know about is metallic bonding. This takes place between 2 metals and forms a giant structure. The electrons in the outer shell of each atom becomes delocalized. This enables them to move around and therefore conduct electricity and heat. There are very strong forces of electrostatic attraction between the ions and these shared negative electrons. This holds it together in a very regular structure and makes metallic bonding very, very strong. Due to these delocalized electrons, this gives us the properties of the metals. So metals are very strong, they are very hard, they tend to have high melting and boiling points, they do not dissolve into water, they are also shiny. They are generally more dense than non-metal structures, and they are able to move over each other, similar to graphite, meaning that metals are malleable and ductile. They are also sonorous when they are hit, and importantly, they can conduct both electricity and heat. For your GCSEs, you need to be able to compare the properties of the metals with the properties of the non-metals. In this tutorial video, we have looked over what an ion is and how they are formed. We have practiced drawing dot and cross diagrams to show the formation of both ionic and covalent bonding, and we have looked at the structure and properties of ionic, covalent, metallic, and the giant structures. So for our big question today, we need to be able to compare the properties of ionic, covalent, and metallic bonding. I want you to have a go at that question now. So, for our answer to the big question, we are looking for the properties of the 3 types of bonds. So, in an ionic bond, we have strong electrostatic forces of attraction. This means that we have high melting and boiling points. Ionic compounds do not conduct electricity when solid, but do conduct electricity when they are molten or in solution. Simple covalent structures do not have strong electrostatic forces. They do have a strong covalent bond between the atoms, however they have very weak intermolecular forces between the molecules. This means that the melting and boiling points are low. They cannot conduct electricity because they do not have any free electrons or ions. Finally, for metallic bonding, we have delocalized electrons with a strong electrostatic force of attraction between the positive metal ions and the shared negative electrons. This means that their bonds are very strong. They tend to have strong melting and boiling points, and they are not soluble in water. Because they have free electrons, they can conduct both electricity and heat. That concludes this video tutorial on bonding. In the next video, Chemistry Key Skills video 4, we will be looking at equations. Within that tutorial, we will look at writing both word and symbol equations. We will look at balancing equations, calculating relative formula mass, and we will look at the theory of the conservation of mass.